In this video, we are going to discuss how to train a predictive model by fitting a distribution using the gradient descent algorithm. This problem appeared as an assignment problem in the Coursera course Mathematics for Machine Learning Multivariate Calculus. As a data, we are going to use the heights data, which is a 100-point data set taken from a population, and there are two variables in the data set. One is an independent variable x that represents the heights of people in centimeters, and the other variable, which is a dependent variable y, which represents the probabilities that a person with that height exists in the population. Now first we are going to start by plotting the distribution or a histogram from the data set, and the histogram looks like a normal distribution. So we'll fit a normal distribution on this heights to find out the probability that a person with that height exists in the data set. So we are going to use the gradient descent algorithm to fit the Gaussian distribution on our independent variable, and our goal is to predict the dependent variable y, which is the probability. So again, the PDF of the normal distribution is given by f, and this is the function that we are going to fit on the data set to predict the variable y. And our goal is to minimize the loss function or the cost function chi-square, which is the squared difference between y, the response variable, and our fitted distribution function f, which is a PDF for the normal distribution. And this is also sometimes denoted as j, as the cost function. Now first we have to find the gradient of chi-square with respect to the variables mu and sigma. So these two actually are the parameters for the normal distribution, and we want to find the values of mu and sigma using gradient descent algorithm. And our gradient vector consists of two elements. One is the partial derivative of chi-square with respect to mu, and that is partial derivative of chi-square with respect to sigma. So the idea behind the gradient descent algorithm is the following. We'll start with an initial random guess for our parameters for the normal distribution, mu and sigma. That will be mu 0 and sigma 0. And at each of the iteration, we are going to update mu and sigma, the parameters, which is collectively represented as a vector theta. We are going to update this vector theta by going down the negative direction of the gradient of our cost function with some learning rate. Now why we are doing that? From the vector calculus, we know that the the direction of the gradient is the direction where any function increases the most. So here our goal is to minimize our objective function chi-square or j. So what do we need to do? We need to go in the negative direction of j in order to find the steepest descent direction. Now here is the gradient descent algorithm. So first we want to start with some random guess for our parameter theta, which is called as theta 0, and then at each of the iteration we are going to go in the negative direction of the gradient, which is the which consists of the partial derivatives of the cost function j, and we are going to go with a learning rate eta, and we are going to repeat this procedure until we have gone beyond a maximum number of iteration, or the theta stops changing sufficiently. And this epsilon 0 epsilon is a constant or a threshold or a tolerance value for convergence. And as we can see that at each of the iteration, basically if we have a convex surface for the cost function, the value of the parameter computed by the gradient descent algorithm at each of the iteration, we gradually arrive at the global minimum if the surface is convex. Now let's come back to our cost function chi-square, which is again the L2 norm of the difference between our variable, the output variable y, and in the PDF, the probability density function that we are going to fit f. And let's compute the functions, the partial derivatives with respect to mu and sigma, the two parameters that we are concerned about. Now, one point that we want to specify over here is that if we have a closed form expression for these partial derivatives, then we would have directly solved the values for mu and sigma that are optimal, for which we are going to achieve the minimum value for our cost function. But in this case, as we can see, by differentiating the cost function with respect to mu and sigma and simplifying the expressions, the expressions that are obtained that are not in closed form with respect to mu or sigma, so we cannot obtain a direct analytic solution. That's why we need to use some numerical algorithm such as gradient descent that will go in the steepest descent direction and gradually going to achieve a local minimum, and that should be our goal. If the cost function is convex, as it is in our case, we are going to achieve or find out the global minimum. Now again we compute the partial derivative with respect to sigma as well, and as we can see, it can also be expressed in terms of our PDF and in terms of the independent variable x, and also in terms of the dependent variable y. So one point worth mentioning is that the learning rate that we have seen in our previous slide. So basically the learning rate has a role for the gradient descent. The learning rate should not be too high, otherwise we may not obtain the convergence and it may lead to divergence of the algorithm. And at the same time, the learning rate should not be too small, because if it is too small, then it will take a long time to obtain the convergence. So we want to find the right value of the parameter eta, or the learning rate, for our gradient descent algorithm. So now, as you can see, we are done with computing the partial derivatives for mu and sigma, for chi-square with respect to mu and sigma. And this is our gradient vector of chi-square, gradient vector of the cost function, or gradient j. You can see that it is again expressed as a two-element vector, and one element is a partial derivative with respect to mu, another is a partial derivative with respect to sigma. Now we are going to use the value of this gradient function in our gradient descent algorithm. Iteratively, in each of the steps of the gradient descent algorithm, we are going to go in the negative direction of this gradient and update our parameter theta, which is a two-element vector of values of mu and sigma. And at the convergence, when you converge, we are going to find the optimal value. Now we can see the Python implementations for gradient descent, as well as how it is used to compute mu and sigma. And these two animations visualize how the convergence is obtained, and at each step of the gradient descent,